Okay, so we've been discussing the renormalization group, which is essentially Kenneth Wilson's insight into how to think about quantum field theory. Now, one of the nicest conceptual things that we can introduce here is the space of all theories. So let's put that down, space of all theories, and let's introduce what this idea is. So think about the quantum field theories that we were discussing. So, okay, good. So if you look at this red boxed equation, we had here an infinite number of couplings. We had GNs, we had CMs, DPs. So there was an infinite number of couplings that you needed to specify to say what your quantum field theory was. So now we're going to introduce a space. This space is an infinite dimensional space. So I'm going to draw a little cartoon of it. So this is an infinite dimensional space. And each of the axes that you have here corresponds to a coupling. So over here, I may have G7. Then over here, I may have C3. Over here, I may have D12. So each of those couplings that we introduced in our Lagrangian correspond to an axis in this space. Okay, so there'll be an infinite number of axes. Picking a point in the space. So if you pick a point, what are you doing? You're picking a value for every single coupling. But if you're picking a value for every single coupling, that means you pick a quantum field theory. Okay? So picking a point in the space corresponds to picking a quantum field theory. Now remember that when we flow from high energies to low energies, the coupling changes. So the quantum field theory changes. So we can view that flow as a trajectory inside this space of all possible theories. And as the couplings change, so we move between points inside this space. So now we get a nice geometrical picture of the renormalization group as some trajectory inside the space of all possible theories. And we'll flow and flow at long distances towards the longer and longer distance theory, towards the theory in the infrared, the theory at low energies, but we'll get to a point where we stop flowing. And this is a fixed point. Okay, so how would we describe this flow? Well, to describe this flow, we have to describe how the couplings are changing. And you know how to describe how the couplings are changing. We would get the beta function. So we would have some scale, mu, which defines the scale at which the theory is defined. And then the beta function for any specific coupling would be beta dg d mu. So it's just telling us how the coupling changes with a change in the energy scale. At the fixed point, what would happen is all of your beta functions would vanish. Your couplings no longer change with scale. And if you remember, we said that when the beta functions all vanish, then you get a conformal field theory. And indeed, all of these fixed points are associated to a conformal field theory. This would be a conformal field theory in the infrared, so at very, very low energies. And so we would flow to a fixed point, and inside the space of theories, there's also points where the trajectories start. So this would be another fixed point, but now in the ultraviolet, and this would be another conformal field theory. And there isn't just one trajectory between the two theories. There would be many different trajectories. So to move away from the fixed point, I would need some operator. That operator would not be scale invariant. So all of a sudden now at low energies, my theory would start to change. So by adding in this deformation to the CFT, which is not scale invariant, so I start off the flow along the trajectory. And there's many different ways of introducing this deformation. So there's many different trajectories that I can get that start from the fixed point in the ultraviolet. And there would be many different ways, there would be many different ways that we could flow to this fixed point in the infrared. So to understand quantum field theory, one of the things that you might want to do is to understand the structure of the space. Of course, you want to understand points inside the space, but you'd like to understand the structure inside the space. What kinds of trajectories do you get? And a large part of understanding what kinds of trajectories do you get would be understanding these fixed points. What fixed points can you have? What sort of a structure do they have? And so on. And that would correspond to understanding conformal field theories. So here's a good reason why you should study CFTs. Another reason to study CFTs is that if you're close to the fixed point, so let's imagine that you're close to the fixed point in the infrared, then nearby that point, we know that the physics will be well described by a conformal field theory. So everywhere inside this red circle, my physics would be basically that of the conformal field theory plus some small corrections. So that's also one reason why conformal field theories are interesting. Now, this point where you get scale invariance at low energy, this is typically associated with a phase transition. This we're going to discuss in a lot more detail. So it's some critical point. And what could this be? Well, imagine that you have, so here's an example. Okay, there's many examples, but here's an example. Imagine you have a system of atoms arranged in some regular arrays. So you've got some sort of a solid, and each of these atoms has a little magnetic moment. Maybe the electrons are spinning in such a way that they give a magnetic moment to this atom. So each atom looks like a little bar magnet. And at high energies, these bar magnets are pointing all over the place, and you've got some interesting microscopic dynamics. At low energies, if you tune things correctly, the temperature and things like this, you can get to a stage where all of these bar magnets start to align, and you get some macroscopic magnetization. That point where you move from the state with no magnetization to the state with some magnetization, there's a critical point where the magnetic field appears. There's all sorts of interesting scaling laws for various quantities. What are the things that determine those scaling laws? It's the anomalous dimensions that we were talking about previously. So it'd be the anomalous dimensions. I think I called them gamma before. Those are the kinds of things that you would want to calculate to determine all kinds of scaling laws at this critical point for this critical phenomenon. Now, notice something that's pretty interesting. There's a lot of completely different trajectories that lead to exactly the same CFT. So what that means is all of these trajectories have different microscopic physics, but because they flow to the same fixed point, they are described by exactly the same long-distance physics. And this goes under the name of the universality of critical phenomena. You can have systems that are completely different. Something like, say, beta brass, it's some sort of an alloy where you have a phase transition, or you have this magnet case where you have a phase transition. And the basic observables are the anomalous dimensions. And these systems that have completely different microscopic physics land up having exactly the same macroscopic physics, which means they have exactly the same anomalous dimensions and exactly the same scaling laws for these critical phenomena. So this is a pretty remarkable prediction. It tells you that there should be universality, that all of these different microscopic physics is described by the same long-distance physics, and it's actually observed in the lab. It's something that we actually observe. So this is one of the other predictions of Wilson's remarkable way of viewing quantum field theory. So maybe that's enough about RG and Wilson's way of viewing things. I think that by now this has motivated our CFT type viewpoint on the subject. What I'd like to do next is let's dig a little bit more into phase transitions and how conformal field theories are relevant for the description of phase transitions.